Engineers tend to work with lots of numbers. For example, a single experiment can result in hundreds or thousands of data points. It's not feasible to provide an individual variable name for each of those data points, so it's easier to group the data points together. That's the idea behind arrays. There's a single variable name that corresponds to a lot of data points which form some logical group. This video introduces arrays, array operations, plotting, and using MATLAB to do curve fitting. An array is a single variable which contains a bunch of numbers. These numbers can then be used as a group, or individual numbers can be extracted from the array. For example, this array, named A, contains 9 numbers. They're organized in 3 rows and 3 columns. The array X has a single row containing 3 numbers. This array Y contains 3 numbers organized in a single column. Individual numbers in the arrays are typically specified by the row and the column in which they can be found. Mathematically, the row and column numbers are indicated as subscripts, separated by commas following the variable name. For example, the element of A in the second row and the third column is 3. This element would typically be specified as A of second row, third column is equal to 3. Elements in one-dimensional arrays are generally referred to with only one subscript. So x sub 2 is 2. And y of 3 is negative 6. Creating arrays in MATLAB can be done in a variety of ways. The approach I'll present here is to create the array by individually specifying every element in the array. To specify that the values being typed are going to be in an array, enclose the values in square brackets. By default, the first value you specify will be in the first row and the first column of the array. Subsequent to this, successive columns are separated by spaces or commas. Successive rows are separated by semicolons or the Enter key on your keyboard. All variables that you create in MATLAB must be assigned a name. The variable name is placed to the left of an assignment operator, which looks like an equal sign, and the values in the array are placed to the right of the equal sign. For example, consider the array B shown here. To create this array, type the variable name B, an assignment operator, and then the values in the array. An open square bracket tells MATLAB that an array is being created. Then type the elements in the first row, 1, 2, separated by either spaces or a comma. To move to the second row, type a semicolon. Then type the elements in the second row, again separated by either a space or a comma. Another semicolon takes me to the third row, and I type the elements in that row. To show that I'm done creating the array, I close the square bracket and press Enter. Now my array is in the workspace. Next, I'll discuss how to access individual elements of an array. Array elements are referenced by putting the row and column in that order of the desired element in parentheses after the array name. The row and column are separated by a comma. If the array has only one dimension, either a single row or a single column, elements can be referenced with a single number in parentheses after the variable name. For a row vector, use the column of the desired element, and if the array is a column vector, use the row of the desired element. Let's do some examples to illustrate this. Suppose I have a 2-dimensional array named A in my workspace, which contains these numbers. I want this value here. In MATLAB, I can type A of 3, 2 to get the element in the third row and the second column. This returns the number 4. Suppose I have a row vector named X. I can get the element in the second column, the number 2, by typing X of 2. Finally, say I have this column vector Y. I can get the third element in Y by typing Y of 3, which will return negative 6. Always keep in mind the difference between the number itself, negative 6, and the location in the array the number occupies, the third element in the array Y. First, I'll define a 2-dimensional matrix named A. So A equals, open square bracket, 1 space 2 space 3 semicolon, 2, comma, 5, space 6, semicolon, 7, comma, 8, comma, 9, close square brackets. Notice that commas can be used interchangeably with spaces to separate columns. Now I'll create a row vector by defining b equals, open square bracket, 1 space 3 space 2 space 6 space 7, close square bracket. Finally, I can create a column vector c equals square bracket 4 semicolon 5 semicolon 6 semicolon 8, close square bracket. If you prefer, you can use the enter key to separate rows. So d equals open square bracket 0 space 1 space 0, the first row, and enter key 2 space 1 space 3, close square brackets. In this case, MATLAB doesn't execute any commands as a result of pressing the enter key the first time, since I haven't closed the square bracket yet and MATLAB knows I'm not done defining an array. The neat part about this is that now MATLAB lets me use this entire group of numbers in mathematical operations. For example, if I type b equals a dot slash pi, every number in A gets divided by pi, and that entire set of values gets assigned to a single variable named b. Notice that I use the dotted version of the division operator here. Without getting into too much detail, the dotted operators perform what are called array operations, or element by element operations. The operators without dots perform matrix operations according to the rules of linear algebra. Matrix and array operations are the same for addition and subtraction, so there's only one version of each of those operators. If I type c equals b plus 2, 2 is added to each element in the array b. I'll talk about array operators more later in this video. Later in the class, after I introduce matrices and linear algebra, we'll talk about the undotted operators. MATLAB also has a lot of built-in functions, all of which accept groups of numbers as inputs. So if I want to take the cosine of all the values in my b variable, I can just type b cos equals cos of b. MATLAB's dotted operators are dot asterisk for multiplication, dot slash or dot backslash for division, and dot caret for exponentiation. The dotted operators perform what are called array operations. This simply means that the operations are performed between corresponding elements of the arrays being operated on. The arrays, or the operands, have to be the same size. The output array will be the same size as the two operand arrays. Now let's look at a few examples to illustrate how these operators work. First, let's look at multiplying two arrays using dot times. The result is simply the multiplication of the corresponding elements of the two arrays. So the element in the first row and the first column is the product of 1 and 5, which is 5. This element is the product of 2 and 6, which is 12, and so on. Dividing two arrays using dot slash is pretty much the same idea. The element in the first row and first column is 1 divided by 5, or 0.2. This element is 2 divided by 6, or 1/3, and so on. The last example is exponentiation. The idea is still the same as the previous examples. The element in the first array is raised to the power given by the corresponding element in the second array. So this element is 1 squared, this element is 2 to the 4th, and so on. Finally, let's use arrays and MATLAB to create a least squares best fit line to a set of data. The data we're using is the speed of sound in water for various values of temperature. The data's in this table. The top row has the temperature values and the bottom row is the sound speeds. We want to use MATLAB to plot this data and then determine a straight line best fit to the data. First, we can define arrays containing the data. I'll create two arrays named temp and SSPD. Temp contains the temperature data, and SSPD contains the sound speed data. The temperature and sound speed data are related by their positions in the arrays. The first value in the temp array corresponds to the sound speed in the first location in the SSPD array, and so on. Before we do any analysis on the data, we want to plot it to see whether we can get a rough idea of what the data looks like. MATLAB has outstanding plotting capabilities. I'll present some of the most basic plotting tools next. A basic two-dimensional plot in MATLAB can be created with the plot command. The syntax is the command name, plot, and the x and y data in parentheses after the command name. X data is an array of data that goes on the horizontal axis, and Y data is an array containing the corresponding values on the vertical axis. An optional string after the data specifies a line style for the plot, symbols to place at the data points, and colors for lines and symbols. Annotating plots is pretty easy in MATLAB. You can put labels on the axes with the X label and Y label commands. And a title can be put at the top of the plot with the title command. The arguments to all of these functions are just a string of text placed in single quotes. The text is displayed on the plot at the appropriate location. If you have more than one line or set of data on a plot, it's a good idea to include a legend describing each set of data. The legend is added with the legend command. Finally, you can add a grid or remove it with the grid command. Now let's put the data in MATLAB and work with it a little. I'll create the temp and SSPD arrays first. Next, I'll plot the data. The plot command accepts two sets of data, an array of the values on the x-axis and an array of corresponding values on the y-axis. I'm going to put temperature on the horizontal axis and sound speed on the vertical axis, so temp comes first in the list and SSPD second. You can also set the type of data points and lines you want to appear on your plot. The codes to specify these styles are placed in single quotes after the x and y data. I'll put red circles at my data points. The code for that is an R, followed by an O. Usually, data is presented without a line connecting the points, so I'm not going to specify a line style. When I press Enter, a figure window is opened and the plot is displayed. To annotate the plot, I'll add axis labels and a title by typing X label, open parentheses, a string saying temperature, comma, degrees C, single quote, and close the parentheses. A label on the y-axis is done similarly. And finally, I can add a title at the top of the plot with a title command. Next, I'll talk about MATLAB's various tools for curve fitting. MATLAB has a variety of curve fitting functions which allow you to fit different types of curves to data in a couple of different ways. One approach is to use the graphical user interface tools available in the figure window itself. Under the Tools option on the menu bar, select Basic Fitting. A dialog box will open that allows you to select a type of curve along with a couple of other options. You can also do curve fitting from the command prompt with the polyfit command. You send the x and y data to polyfit along with the order of the polynomial you want to fit to the data. The polyfit command fits a polynomial of order n to the data. A straight line is a special case of a polynomial where n is equal to 1. If n equals 1, the polyfit returns the slope and y-intercept in an array. The slope will be the first element in the array and the y-intercept is the second. Now I'll demonstrate use of both of these approaches. The plot window itself allows you to perform some basic analysis of the data. To fit a curve to data, click on Tools and select Basic Fitting. In the dialog box that opens, you can select the type of line you want to fit to the data. I think I'll try fitting a straight line to the data, so I'll click Linear. And the line that represents the data is shown on the figure. I'd also like to see the equation for the line that fits the points, so I'll select Show Equations. The equation is added to the figure. The dialog box also shows the equation. P1 is the slope of the curve, and P2 is the y-intercept of the data. This interface makes it easy to check different types of curve fits. Let's look at using a cubic equation to represent the data. Now I'll close the figure window and see how to do the same thing at the command prompt. To fit a straight line or a first-order polynomial to the data, I'll type P equals polyfit of temp, comma, SSPD, comma, 1, close parentheses. MATLAB returns this array. The first element is the slope, and the second is the y-intercept. Now I'll calculate the curve fit at the x values of the data points by typing SSPD underscore fit equals P of 1, the first element in the array is the slope, dot times temp, the array of temperature points, plus P of 2, the y-intercept. Now I'll plot both the data points and the curve fit. So plot of temp, comma, SSPD, comma, quote, R0, plots the data with red circles at the data points, comma, temp, comma, SSPD underscore fit, comma, quote, K, colon, end quote. So I'm plotting the fit as a function of temperature with a black dotted line. Now I'll add a title, an x-axis label, and a y-axis label using the same commands as last time. Finally, I'll add a legend with legend, open parentheses, single quote, data, single quote. So the label on the first set of points will be data, comma, single quote, curve fit, single quote. The second line will have the label curve fit. The legend command has as many labels as there are data sets on the plot. The order of the labels in the legend command corresponds to the order of the data sets in the plot command. Our final figure looks like this. Arrays are fundamental to MATLAB. MATLAB's built around the idea that numbers are grouped together, so most MATLAB functions, like plotting and curve fitting, will use arrays.